Hello everyone. In this video we're going to review chapter 5, which is when we learned how to differentiate and integrate logs, mainly natural log and exponentials, normally e to the x. And so the first thing we're going to do is just review some log and exponential facts and rules that we use. So hopefully by now we all remember that when you see ln, natural log is how you read it, and that is the same thing as just saying base e. So if it helps you, you can always put a little base e there to remember. But that's what it's telling you, that it's log base e. So if you have y equals natural log of x, and let's say you needed to solve this for x, the way you learned back in the day was around the world, and you can still do around the world. Sometimes it gets confusing. So really what you're doing is, if you're trying to get x out of the log for whatever reason, if it's inside a log, you do the opposite. You raise it to the power of whatever the base is. So you would do e to the base, since this is natural log, which is base e, we take it e to the power of that natural log. And whatever you do to one side, you got to put base e over here. So what happens is that these would cancel when this is the same base and it's being raised to that same base. So then you're left with e to the y equals, these cancel, and you're left with just x. So x equals e to the y. So that is one way you could go. If you're solving for the variable that's inside the log, you raise it to that base to cancel it out. If you're solving for the variable that's in the exponent, then we would take it to the log, in a different color. If we're solving for y in this case, well then, because it's the exponent for base e, then we would take log, natural log, that's the same base. That means you gotta do natural log over here. So then what happens here is, because it's natural log, which is base e, and this is the same base on the inside, those cancel, and you would be left with just y equals natural log of x. So this was just kind of going opposite ways. If you're solving for the variable that's inside the log, you got to raise it to that same base on each side. If you're solving for the variable in the exponent, then you got to take the log of that same base on each side. So I hope that kind of makes sense. But it is the same result as around the world if you prefer to think of it like that. The next thing we're going to talk about is just the graphs. You should have these graphs memorized because I really do think it helps. So what is a log graph? Which honestly, normally what we care about is the natural log of x graph. But these two graphs will look the same. It has a vertical asymptote on the y-axis and goes through 1 on the x, and it goes up like this. And what does an exponential graph look like? Which that base could be anything, and it's going to look like this. It doesn't necessarily have to be e, but it includes e. Is it has a horizontal asymptote on the x-axis, and it goes through 1 on the y, and it goes along forever to the left and then curves up. And these points, maybe I should put them. This would be 0, 1, the y-intercept, and this has an x-intercept, 1, 0. Okay. So what does that mean for exponential? Is that it can never equal a negative, right? An exponential is always a positive. Even if you plug in a negative x value, because our exponent rules, that's just going to get smaller and smaller, but it's never going to get negative. And here's some more log facts that help us out. Anytime you have a 1 on the inside, no matter what that base is, so natural log of 1 would just be 0. If it's natural log of e to the something, it's just going to equal that something, because again, this is base e, that's base e, so it's like they cancel, and you're left with just the exponent. And same thing here, it's like what we did up here. If it's e to the power of natural log, because those bases are the same, they cancel, and you're left with just the x. So those facts will help you in your algebra in some questions that involve natural log and exponentials. Other thing is your expanding and condensing rules, right? So if you have natural log you have two things being multiplied on the inside, you can expand it, oops, I don't know what I'm writing there, to natural log of the first thing plus natural log of the second thing. So that means if you're condensing, if you have natural log of A plus natural log of B, you can condense it to be 1 natural log and multiply the insides. Now if you're adding on the inside, you can't do anything with that, you just got to keep it. So if you have natural log of A minus B, we can expand that to be the natural log of A. Why did I put minus? Dang it. That's supposed to be divided by on the inside. Let me rewrite it. Natural log of A divided by B is going to equal the natural log of A minus the natural log of B. I'll put it here as well. I kind of saved that and made it A over B. Because if it was subtraction, you can't expand that. So these are the same thing, I just messed up. And then the last expanding rule we have is if you have natural log of A to the power of something, if you have an exponent on the inside of a log, you can bring it out and make it a coefficient and just multiply it by the log. So that would just be A now on the inside. Which also means if you have a coefficient in front of your log, you can condense it and put it inside as an exponent. So these work both ways. So then that's the review of the algebra pre-cal aspect. Let's get into actually calculus. So here are our rules for differentiating. If you're taking the derivative of e to the x, we know that that just stays e to the x. Now if it's e to the power of something more than just x, that u just represents something more than x. It could be, you could also use like f of x or g of x. Well, you're going to keep it the same to do the derivative of e, but then it's chain rule times the derivative of what was in the exponent, which we'll call that u prime. So if that was e to the 2x, you would write e to the 2x times the derivative of 2x, which is 2. And then the derivative of natural log is 1 over x, which means if you have more inside your natural log, you got to use chain rule. So you do 1 over whatever the inside is times the derivative of the inside. Just to kind of clarify, this is going, derivative of natural log is 1 over x. So what if you had derivative of 1 over x? Is that natural log? No, it doesn't work that way, right? The integral of 1 over x is natural log. But here, if you're going to do derivative of 1 over x, you would just use power rule. We would change this. So we haven't taken derivative yet, but if I could move this to the top by making x to the negative 1, and now I could take the derivative of that, bring my exponent to the front, and then subtract 1, which would be negative 2. So be careful about that. The derivative of natural log is 1 over x, but the derivative of 1 over x, you use power rule. The only time you don't do power rule is, let's say if you're integrating and you get 0 once you do your plus 1, that's your red flag. So here's an example if we're going to do the derivative of this. You could go about this a couple different ways. We could bring that 3 out. Since it's on everything inside the log, we could expand it. Or if you kept on the inside, you could still get the right answer. So I would encourage you to pause the video here, do this problem, and then just see if we get the right answer. You don't have to change the way you do it. So if you forgot that you have that expanding rule, I feel like that's probably what most people would do, is they would just start with doing 1 over the inside. So that inside is x minus 3 cubed if you didn't expand it. And so then we got to do times the derivative of the inside. So the inside is whatever you wrote on the bottom. So now we're going to do this. We're going to bring the 3 to the front, which again, you're still using chain rule. Because you still have something, the x minus 3, inside something else, the cubic. So we bring the 3 to the front, keep the inside the same, to the power of 2, and now you can do the chain rule one last time. The inside of this, which the derivative of x minus 3 would just be 1. So if I write this all on top of each other, because right, we could put this over 1 and this over 1, so these go on top. 3x minus 3 squared over x minus 3 cubed. Which, if we think about this, x minus 3 squared over x minus 3 cubed, you don't have to show this, but just to, if you know what you're doing and you simplify it in one step, you can. But I'm going to show you what does that mean if we expand it. That's 3 times x minus 3 times x minus 3, and then x minus 3 cubed on the bottom. So that means 2 of these crosses off with 2 of these, so you're left with 3 over x minus 3. Could you have used exponent rules here as well? Right, 2 minus 3 is negative 1. So since it's negative, that means it's on the bottom. And that is your derivative. That's as far as you can simplify. So on page 21, it reviews integrating, so going opposite. So if we think about this, it should make sense because we just said the derivative of natural log is 1 over x. So then the integral of 1 over x, whose derivative is 1 over x? Natural log, right? So we know the integral of just 1 over x should equal the natural log, and now you normally use absolute value here, plus c. And that means here, if you have the integral of the derivative of whatever you have on the bottom, honestly, you would use u substitution here, but that's going to work out to be ln of the inside, and you would see that using u substitution with u equal to the denominator. Right, so our strategy for u substitution is if you have something inside of something else, you make that the u, or if you have something inside an exponent, or if you have stuff on the denominator. Those are your options for u. And then that means the integral of e to the x, if the derivative of e to the x is e to the x, then the integral is also e to the x plus c. And if you had the integral of e to the u, you would want to make sure you use substitution, or I should say u substitution, with u equaling exponent. So don't forget that. If it's not just x, don't go too fast. Even if it's just 2x, you still need to think about it using u substitution, because that's going to add a coefficient that you're not going to have if you just straight go e to the x. So here are some examples. So for this one, we look at this, and you have a couple different options. So I know I'm going to need u substitution. What should I make my u? Because technically my secant is being squared, so I could make secant u. But if you go do that, you're going to get stuck, because then your du is going to be pretty messy and it won't replace the tangent. So actually what you would do here, because you should recognize, we know that secant squared is the derivative of tangent. So it's matching this format where the derivative is over the original. So if it's that case, then let's try making u the denominator. So that makes du, the derivative of tangent, is secant squared dx. So we see that we could box the secant squared dx, and all that's going to get replaced with du. So then we're going to rewrite our integral. If you want to pull this to the back, you can, and make that 1 over tangent x. And then that, when you pull that to the back, that's why it's just 1 over, and then you have times secant squared x dx, which is what we boxed. So now we changed it to u. 1 over u d, all that's boxed just equals du. And now we know the integral of 1 over u, which is just like an x, is natural log of u plus c. And then you replace your u, so that's natural log of a tangent x plus c. Okay, on the next one, this is kind of messy. So you might think about a couple different things on this problem, but best thing would be to notice that this is x squared plus 1, and you have an x squared plus 1 up here, right? So you could rewrite this problem to be the integral, I'm just going to rearrange the top to make it x squared plus 1 and then plus x, because addition, you can rearrange it as long as you keep the sign in front of each term the same, over x squared plus 1. So now we can see that this is equivalent to this. So we can separate the numerator as long as we keep the denominator together. So we can divide x squared plus 1 divided by x squared plus 1, and then we can also divide x by x squared plus 1. Okay, that is legal as long as we keep this denominator, the whole denominator together, we don't separate it. So what would that look like? It would be the integral of x squared plus 1 over x squared plus 1. Then you have plus x over x squared plus 1. So why did we do that? Let's see, because we know that anything over itself would just be 1 plus x over x squared plus 1. Oh, and I forgot my dx right here, didn't I? Okay, so we know we can integrate 1 pretty easy. Now here, we know we'll probably need to use substitution because we got more stuff on the denominator. So let's see if it works out. And we can't bring this to the top, this x squared, because of this plus 1. So if we just set up use substitution just for this term. Okay, when you use substitution, you have more than one term. You don't have to use that one because technically we can integrate each term separately. If you want to show separating them and give them their own integral, you can, or you can just kind of work with this term in your head. So we make u our denominator, J-Mac. So then our du is going to be 2x dx. So if we notice, we have this x dx. So we need to move over the 2. So when you divide by 2, it becomes 1/2 du equals x dx. So you can replace x dx with 1/2 du. Okay, so then if I'm going to go ahead and just in red kind of make my work for just this u substitution and integrate this, and then I'll go and write what that actually equals. So if I want to rewrite this, so I'm just focused on the integral of x over x squared plus 1 dx. I'm ignoring this 1 because I can integrate that separate. So this is what I boxed. So I can bring that to the back. And I have 1 over x squared plus 1 times x dx. So when I change this to u, it's 1 over x squared plus 1 was u. X dx, be careful, is not just du, but 1/2 du. So that 1/2 is a coefficient. So you can pull it out and put it in front of the integral. So then the integral of 1 over u would be, you still have your 1/2, and then that's natural log of u plus c. So what was your u? It was x squared plus 1, so this is 1/2 natural log of x squared plus 1 plus c. So that's for the second term. So now we're going to integrate. What's the integral of 1, though, for the first term? Whose derivative is just 1? That would be x plus the integral of this second term we got down here, 1/2 natural log x squared plus 1, and then put your plus c at the end. And that would be your answer. So that one you kind of had to think outside the box, definitely, to get started. Okay, and well, not last, there's some other things at the bottom, but kind of switching gears, another thing we covered in chapter 5 was inverse functions, how to find the derivative value of an inverse function. So this only works if f and g are inverses, if they tell you. If they never said f and g are inverses, you cannot use that formula. So I'm going to write that down. If f and g are inverses, then g prime, so how I would word this is the inverse, because I'm going to treat g as the inverse of f, so the inverse derivative equals 1 over the original derivative of the inverse value. Okay, so maybe if you write off those words, it might help. You can also put it in this inverse notation, right? Another way is if g is the inverse of f, then g equals f negative 1, right? That's the notation for inverse. So another way you could write this formula is the inverse, but now this is where it gets confusing because it's inverse derivative, and that's just messy because you have the inverse symbol and then you have the prime derivative symbol, equals 1 over the original derivative of the inverse value that you're talking about. So that's derivative, that's inverse. Those look very similar, so that's why this is better, but this kind of makes more sense in terms of it being inverse. So here's a problem. It says f of x is x cubed. Find f negative 1 prime of 8. So let's use this setup. So we know that f, I'm going to come over here and write it. Actually, no, I'll go in order. F negative 1 prime, so the derivative of the inverse, that's when you use this formula. If you're finding the derivative of an inverse function of 8 will equal 1 over the original prime of the inverse value at 8. So your first step is you got to find this inside part, the inverse value at 8. So that is an x value for the original. So remember, this value they give you, that means if it's the x value for the inverse, then it's the y value for original. So what we're going to do is to find the inverse value at 8, we're going to plug in 8 for the y value of the original. So that would be, you can walk by if you need to. 8 equals x cubed, so then we're going to cube root it. And the cube root of 8 is 2, so x equals 2. So that means for the original f of x, the order pair is 2, 8. So that means for the inverse value, you switch it, right? For inverse, you switch x and y, so now that's 8, 2. So what we just found is when x is 8, the inverse value is 2. So now I'm running out of room. I'm going to use another sheet of paper. So this would equal 1 over f prime, the inverse value at 8, we just determined is 2. This x value from the original is the inverse value. And now we just need f prime of 2. Well, we have f of x, you need to go over to the side and get f prime, which would just be 3x squared. So then that makes f prime of 2. What is that? 12. So the answer is 1 over 12. So these can get kind of backwards in your head, so you got to be careful that you're thinking about the right x or y value. And so then if it's free response, it would probably be a table. So I think the tables are easier. So let's set this one up, the same formula. It'd be 1 over f prime of the inverse value at 3. So how do we get the inverse value from a table? It's the same idea. So that x value that's on the inside is the y value for the original. So this 3 is the y value for original, which is f of x, which the original is f of x. So you're going to look for 3 for the y value, f of x. And so what is that x value? It's 1, so that is the inverse value. So what also might help is on these tables, if it's this type of problem, go over to the side and create an inverse table, because we don't have f negative 1 on here. So how do you create an inverse table? Well, you don't need the derivative, and you just switch all these x, y values. So x is 0, inverse is -1, x is 2, inverse is 0, x is 3, inverse is 1, x is -1, inverse is 2, x is 1, inverse is 3. So now we want the inverse of 3. So now you can go, now that we've switched it, you go to the x value is 3, the inverse value is 1. It's just the same thing we did here, but if this makes more sense, go ahead and do that. So that'd be 1 over f prime. We just said the inverse at 3 is 1. So now we need 1 over f prime of 1. So you go back to the original table. When x is 1, go to f prime, which would be 2. So, I don't know why I'm putting equals. That's your answer, 1/2. So if you look at this table, notice we're staying in the same column. That x value is actually going to be the y value for the original, and so then this is the x value you're at, and then you're getting the derivative at that point, and it goes on the denominator. Okay, last thing, I really don't think this is going to come up, but it could come up, is if the base isn't e, right? How do you do the derivative if the base isn't e, but it's still exponential? X is still in the exponent. X is in exponent, but base isn't e. It's the same concept, so now I wrote too low. I'm going to write it right here. So you still keep it the same, a to the power of u times whatever is the exponent. That part's the exact same as e. But now, because it wasn't base e, you got to do times the natural log of the base. That's like converting it to be base e. And so if you're integrating, same thing, when you integrate, it'd be 1 over natural log of a times a to the u. Which, like, that one I really wouldn't worry about. I should have put it integral.